Okay, this standard talks about one-sided limits, C.1.5. So we talked about the notion that a limit has two sides to it when you approach the point in question or the value in question from the left and from the right. And by the left and right, what I mean is, let's take for instance the value x equals, let's take for instance the value x equals 2, negative 2. So that value, if we look, has a if I plug in negative 2 to the function, I will get an answer of negative 1. That's right here. But the function from the left and the right intends to get to positive 4. So when we talk about a limit, again, we're talking about the function's intention. So when a limit approaches the same value from the left and the right, the limit does exist, even if the function is not that point. So here's kind of how we would write that. So the limit, if we were looking at this, as x approaches negative 2 from the left, we would say of f of x, let's say this function is f of x equals 4. Okay, so the limit as x approaches negative 2, I'm sorry, from the right, and so this is the symbol indicating right here from the right. This is the symbol indicating from the left of f of x is also 4. And when we say from the right and from the left, we literally mean starting on the right, you travel from the right-hand side. So you take your right hand or your right index finger and trace the graph from the right towards the point you're going towards. And for instance, same thing on the left. You actually literally start with your left hand or left index finger and trace the graph towards the point in question. So you follow the line of the graph, don't follow the point. So the limit as x approaches negative 2 from the left is 4. The limit as x approaches negative 2 from the right is also 4. So that we can say the limit as x approaches negative 2. And we don't say the two-sided limit, but we have to understand that it means the two-sided limit of f of x does equal 4. However, f of negative 2 equals negative 1. So because the limit as x approaches negative 2, x does not equal f of negative 2, then the function is not continuous. And that is one of the main theories, one of the main ideas behind continuity. So we've understood continuity in the past as, you don't have to pick your pencil up when you draw a function. Well, in this case, we're actually looking at the limit. So if the limit and the function at that point equal the same thing, then we say the function is continuous. If either one is off, even by just a minuscule amount, the limit, it's not continuous. Okay, so I wrote a little more than I wanted to, so let me erase what I had here. That's continuity. That has to deal with another standard, so we won't get into that just yet. All right, so we found out the limit as x approaches negative 2 does exist. Let's look at the limit as x approaches positive 2. So the limit as x approaches 2 from the left of f of x, and the limit as x approaches 2 from the right of f of x. All right, now we said we literally take the function line from the left. So here's 2. And here is the left side of 2. So I'm going to follow this line towards wherever it's headed. All right, it's headed towards negative 4. So as the limit as x approaches 2, this one, from the left is negative 4. All right, so again, I'm going to find 2. And this is the other part of the function here. It's on the right-hand side of it, right here. So I'm going to follow it towards 2. And it looks like it's also heading to negative 2. You can see it's no intentions to do otherwise. So negative 2. Now here's a case where the left-hand limit does not equal the right-hand limit. So if we were to say the limit as x approaches 2, the general limit, otherwise known as the two-sided limit, so the general limit as x approaches 2 of f of x does not exist because the functions can't agree on where to go. So we have, again, from the left side, heading down here to -4, and from the right side, heading over here to -2, they don't intend to meet at the same spot, so the limit, the general limit, does not exist. All right, and let's look at one other type here. So let's look at the second graph, and we'll say the limit, and this is -3 here. It's a little faded. So the limit as x approaches -3 from the left, let's call this function g of x, and the limit as x approaches x approaches -3 from the right of g of x. Okay, so we quite literally find -3 and go into the left. So here is somewhere on the left of -3, and we follow the function towards where it's headed. It's headed towards 2. So from the left, the limit is 2. Literally go to the right. So here's some piece of function to the right hand side of -3. We follow it to where it's headed. It looks like it's headed to +4. What we learned from the previous one is that if the left and the right hand limit do not agree, then the general limit, g of x, does not exist. So the limit at -3 does not exist. Let's look at the limit as x approaches +3. We'll do that one up here. From the left, and the limit as x approaches 3 from the right. All these are of g of x. Alright, so quite literally find a place on the function to the left of 3, somewhere around here. It looks like it's headed to 3. Somewhere on the right, here's some function to the right. We follow it in. It looks like it's actually headed to 3 again. So the limit, the actual limit, as x approaches 3 of g of x, is 3. But notice that g of 3 is 0. All right, that's okay. The limit exists. Function is not continuous there, but the limit exists. All right. And let's look at 1. Something's curious happening at 1. So if I look at the limit as x approaches 1, and I'm quite out of space, I'll just put it on the bottom here. So the limit x approaches 1 from the left and from the right. So we'll do from the left and also the limit as x approaches 1 from the right. So let's handle the right first. So here's some piece, here's 1. And here's some piece of function to the right. The function intends to go down, and it keeps going. It's never going to hit. It's never going to get to 1. So it looks like it's headed to -infinity. And we can say that that the function itself, the values are headed to -infinity. Let's look at it from the left. Here's somewhere to the left of 1 on the function, and we follow it where it's going. It also is headed to -infinity. So since the left-hand limit and the right-hand limit are both headed to -infinity, we say that the limit is, the answer is -infinity. There are some texts that would say does not exist. I don't know if it's quite proper to put that it equals -infinity because you can't quite quantify infinity. But since both pieces of the function are headed to -infinity, we would say that the two-sided limit is headed to -infinity, because since both pieces are headed that way. So that's kind of a tricky one, but if both pieces of the function are headed to the same place, then go ahead and be confident that that's what the limit would be. So what would this look like in a problem form? Well, you might see a graph like that, all split up on the test, and they might ask you some tricky questions about it. But just remember your rules and what you're looking at, what pieces of the function you're looking at, and you should be fine. The graphs are generally easier part to look at. So here's a function. Trying to be done in the next couple minutes here. For what values of x is f not continuous? Well, to determine continuity, and we're not there yet, but we just talked about it a little bit. A function has to be continuous if the left limit and the right limit exist, if they agree. So that means if the limit exists, and also the function exists at that point. So if they equal the same thing, then it's going to be continuous. And the way we can figure that out in a piecewise function is we can just substitute the interval endpoints and see if we get the same answer, because that would be the same as telling us where that function is headed for. So I'm going to do the sine of 0 and 0 squared and check. So the sine of 0 is 0, 0 squared is 0, and those are equal. So this would be to the left, just like saying this. And this would just be like saying okay, because the function is defined to the left less than 0 as this, and to the right of 0 as this. So if they both meet at the same point, if the functions are both headed to the same point, namely plug in 0 to both of them, then we know that they're going to meet right there. So this again doesn't have a limit function, like isn't showing you limit, but we know that it is that's what we're looking for. Alright, so that's where that is continuous, so that's not it. Alright, let's check the next one. So we're gonna plug in the 1's for x squared and 2 minus x. So 1 squared is 1, 2 minus 1, oops, sorry, is 1. That checks out as well. So that's not the one. Check out 2. So we'll do 2 minus 2 and 2 minus 3. So that's 0 and that's negative 1. Those do not equal. So 2 is a possibility, and that's the only possibility left. So we would say that one. So when it says continuity, you're usually looking for the function value, and especially on a piecewise function, you're looking for the left side and the right side to be the same answer. So again, no limit, like no formal limit here showing in the function, but you know you're looking at the left and the right hand sides.